All right, so let's talk about positron emission. So in positron emission, the mass number of the new nucleus is the same, but the atomic number decreases by 1. And remember, where essentially do we get a positron from? A positron, sorry about that, didn't have the pen ready. In a positron, a proton is changed into a neutron. And let's fix one more aspect of this. There should not be 2 arrows there. That should be a plus sign. So let's get that out. Okay. So in positron emission, a proton is changed into a neutron. So what happens to the mass number? Well, if we're going to have 1 less proton, the mass number is going to go down by 1, but then a neutron is generated. So the mass number is going to go back up by 1. So essentially, there's no overall change in the mass number. But because there's going to be 1 proton less, that means the atomic number has to go down by 1. And again, in the atomic symbol for a positron, the mass number and the atomic number that we have for it reflects those aspects to give us the right answers and the right results of what's going to form. So let's take a look at a couple of examples. In the first one, we have boron with a mass number of 8. That is a positron emitter. When it releases a positron, what does it become? All right, so let's start with the atomic numbers first. On the reactant side, we have an atomic number of 5. On the product side, okay, what plus 1 is going to give us 5? And the answer to that would be 4. So our mystery substance has an atomic number of 4. Let's go to mass numbers. On the reactant side, we have an mass number of 8. On the product side, what plus 0 is going to give us 8? And of course, the answer to that is 8. And then using the atomic number to identify our mystery substance is beryllium, Be. Okay. On the second example, again, now let's take a look to try to find what the positron emitter was. That releases a positron to become xenon with a mass number of 127. So let's start with the atomic numbers first. On the product side, we have 54 plus 1. 54 plus 1 is 55. So our mystery substance has an atomic number of 55. For the mass numbers on the product side, we have 127 plus 0. 127 plus 0 gives us 127. Again, using the atomic number to figure out what the identity of our mystery substance is. The only element in the periodic table with an atomic number of 55 is cesium, Cs. Okay, so those are your positron emitters, positron emission. Okay, gamma radiation. So in gamma radiation, energy is emitted from an unstable nucleus, usually indicated by an M following the mass number. So in the example on the bottom, let me put an M, okay, to illustrate that would be the unstable nucleus. Now, as we talked about, there is no change in the number of, and let me just cross that out. There's no change in the number of protons or neutrons in the nucleus of an atom that releases a gamma ray. Essentially, we talked about the idea that a messy room gets cleaned up, but you're not throwing anything out of the room, okay? Or you're not changing exactly what's in the room. All you're doing is cleaning it up. So in terms of this this nuclear equation here, what would be the identity of our mystery substance? Well, it's still going to have an atomic number of 13. It's still going to have an atomic number, mass number of 27, and it's still going to be aluminum. The difference is this aluminum is going to have a lower energy, more stable nucleus, where the aluminum we started with has a higher energy, less stable nucleus. And the only way to really indicate that, and I haven't often done it in the past, but I can see the merit of it, is to put an M following the mass number. Not exactly sure what the M represents. I'd have to look it up. But it really sort of reflects the fact that, inside the nucleus, you have your protons and your neutrons, and we're trying to clean that up. So maybe M stands for messy. It doesn't stand for messy, but maybe just another idea of thinking about it. All right. Okay. Even if I didn't give you the M, and you had 2713 Al going to something plus gamma, your answer would still be 2713 Al. So its atomic symbol would not change. All right. So on the next slide, you have a summary of the different types of radiation. Alpha, beta, positron, and gamma emitters all emit radiation, and new and more stable nuclei are produced. It talks about changes in a mass number and atomic number of the substance, the radioisotope, as these different particles and pure energy, the different forms of radiation are released. Okay, so as I mentioned, one other thing we'll look at with nuclear reactions and nuclear equations is actually producing radioactive isotopes. A lot of the radioisotopes that exist have usually higher atomic numbers associated with them. However, it is possible to take a non-radioactive isotope and make it into a radioactive isotope. And basically what we do is we essentially bombard that non-radioactive isotope with small particles, like alpha particles or beta particles or neutrons and such like that. So when we say bombard, really what it means is just hit it with it, put these things in a chamber and then hit it with that particle over and over and over, zap it in a sense with that particle over and over and over and over again. This process of essentially taking a non-radioactive isotope and making it into a radioactive one is what is known as transmutation. Right. So in our first example, we have nitrogen with a mass number of 14. Okay. Nitrogen with a mass number of 14 is a non-radioactive isotope. If we bombard it with alpha particles, we're going to convert that into a radioactive isotope, and protons are going to be released as well. So the question is, what is the identity of this new radioactive isotope? So we're going to follow the ideas of balancing nuclear equations that we have talked about. Let's start with the atomic numbers first. On the reactant side, we have 2 plus 7. So 2 plus 7 is 9. On the product side, what plus 1 gives us 9? So essentially, we'll do a little work on the side here. 2 plus 7 has to be equal to question mark plus 1. So the question mark for the atomic number has to be 8. 2 plus 7 is 9. 8 plus 1 is 9. Now, for the mass numbers, we have 4 plus 14. And that would have to be equal to question mark plus 1. So 4 plus 14 is 18. What plus 1 is 18? 17. And therefore, again, using the atomic number to identify the substance, the only element in the periodic table with an atomic number of 8 is oxygen. So here we're talking about oxygen with a mass number of 17. Okay. In the second equation, we start out with aluminum with a mass number of 27, which is non-radioactive. Again, we're going to bombard this with alpha particles. Now, in this case, what we're being told is we're being told that we're going to get silicon with a mass number of 30, which should be the radioactive isotope. But what we want to figure out here is what else is generated in the process. Doesn't change what we're going to do. So for our atomic numbers, 2 plus 13 should be equal to 14 plus question mark. 2 plus 13 is 15. 14 plus 1 is 15. So our mystery substance has an atomic number of 1. Now for the mass numbers, 4 plus 27 should be equal to 30 plus question mark. 4 plus 27 is 31. 30 plus 1 is 31. So our mystery substance has an atomic number of 1. So if I think about it, what has an atomic number of 1 and a mass number of 1? It has to be a proton. So I could use the chemical symbol of H, or I didn't mean to write a 4 there. I could also use, if I wanted to, 11p. And remember, it wouldn't be the same as a hydrogen atom, because a hydrogen atom has 1 proton and 1 electron. Overall charge is 0. A proton has 1 electron. Sorry, a proton has 1 proton and no electrons. So the overall charge is +1. But because we have an atomic number of 1 here, we could use the chemical symbol of H, which is to recognize it's not a hydrogen atom, it's a proton that fits here. So sometimes, and not only in these types of problems, but in the other types of problems we saw earlier on in these videos, in terms of balancing, sometimes you have to be able to identify the particles. So that's why knowing the atomic symbols for neutrons and protons is important as well.